Welcome to this lecture. Before we proceed with the discussion of this lecture, let's first quickly recall what we have done in this week. So we have finally finished the identification between distribution functions on R and the collection of probability measures on the measurable space real line together with the Borel sigma field. So what we have seen is that given a probability measure, we can construct the distribution function as per the usual definition. But on the other hand, given a distribution function, you can construct back the probability measure. So this correspondence gives you the complete identification between these two classes of things. Alright. And we have also seen that this correspondence also extends to the class of Lebesgue measures, which we discussed in the previous lecture. So what we have seen is that this extension is connecting to the class of non-decreasing and right continuous functions on the real line. Okay, so here we are considering any function on the real line taking values in the real line. Alright, so we consider such functions but with the properties that they should be non-decreasing and right continuous. And what we have seen is that for each Lebesgue measure we can construct corresponding such functions with the appropriate parameterization, but then on the other hand, given such a function, you can reconstruct the measure. Alright, so the main connection between these measures and the functions come in this following format, that the measure of left open right closed intervals AB is simply the increment of the function at the endpoints. Okay, so if the interval is open A to closed B, the increment is simply f of B minus f of A given the function capital F. Okay, and using that we followed the standard settings, like we extended by finitely additivity, and then we proved certain countable additivity by verifying continuity properties and extended it to the whole Borel sigma field by the characteristic extension theorem. So in this way we have constructed a large class of examples. So given any non-decreasing and right continuous functions, you can now construct such measures. Okay, so and what we mentioned was that this covers all probability measures, all finite measures, and certain special class of sigma finite measures which are known as this Lebesgue measures. And as a consequence of this construction, we looked at the special example which we called as the Lebesgue measure. So in this lecture we are going to focus on the properties of the Lebesgue measure, and let's now move on to the slides. So again, a quick recall. So in the previous lecture we discussed this construction of this class of measures called the Lebesgue measures on the real line, but this correspondence was through this class of non-decreasing and right continuous functions on the real line. This construction generalized this correspondence between probability measures and the corresponding distribution functions. Now let's move on to the special example that we just mentioned. So we look at this Lebesgue measure, and this Lebesgue measure appears as a special example under the Lebesgue measures. It's for the specific function, the identity function f of x mapping to x itself. So this is a nice non-decreasing and right continuous function, and therefore as per the construction you will get a measure. So the measure that you get is called the Lebesgue measure on the real line. Okay, and now we are going to focus on the various properties of this measure. So first of all, the first thing that you should notice is that by construction, the length of this left open right closed interval AB, for any AB that is varying in this range, you get the length as B minus A, or the size that is attached to this is simply B minus A. Okay, so therefore you will immediately observe that the Lebesgue measure, which we now denote by lambda, so this lambda associates the usual length on intervals. Okay, so specifically for this left open right closed intervals, we have verified that by construction itself we immediately get that the length or the size of this is the usual length. Okay, alright, so let's now move forward and see what are the other interesting properties. So now pick any point in the real line, call it small x, and consider this kind of a left open right closed interval. So what do? We look at x minus 1 over n comma x. So this is the left open right closed interval. Now observe that if you choose the value of n as 1, so that is the largest set in this collection. So as n varies, this sets shrink, right? So let's look at the case n equal to 1. So then you get the interval left open right closed interval, which is x minus 1 to x closed, right? But as per the definition of the Lebesgue measure, what is the size of this? This is simply the length, which is 1. Okay, and this is finite. Okay, so now observe that this sequence of sets, they are decreasing. So therefore you could apply continuity from above provided this finiteness condition holds. So which we are now explicitly verified that for at least one of the sets in the sequence, the size should be finite. Okay, so here we apply this proposition 10 of week 2, which talks about continuity from above, provided there is a finite size set, right? So here we have verified that there exists a set with finite size, and therefore we now observe that the continuity from above should be true for this sequence of sets. But now this sequence of sets decrease and decrease to the singleton set small x, and therefore you will immediately claim by the continuity from above for this Lebesgue measure, you get that the length of this singleton set is exactly the limit of the individual sizes or the lengths of these intervals. But then what are the sizes here? The sizes are simply 1 over n, and as n goes to infinity, this goes to 0. So by this argument we have verified that length or size of singletons under the Lebesgue measure is 0. Alright. So this is an important observation now. But then you can use countable additivity or finite additivity to go from singleton sets to finite or countably infinite sets. Right? Because any finite or countably infinite set can be thought of as a finite or a countable infinite union, disjoint union of singleton sets. So just take each individual element in the set and think of it as the disjoint union of those things. So you will obtain any finite or countable infinite set on the real line. But then you use the finite or countable additivity of the Lebesgue measure lambda, and therefore you will immediately get that the length or the size of such sets, if it is finite or a countable infinite set, then you will immediately get that the length or the size is 0. Okay, so this is simply using the fact that the length of singletons is 0. Great. But then you will immediately use this fact that singleton sets has measure 0 to make other interesting observations. Like you start with this closed interval now. So we had already verified that the length or the size of left open right closed interval was exactly the usual length. But then you look at this closed interval and write it as a finite disjoint union of this left open right closed interval and the singleton involving the left endpoint. But use the finite additivity of the Lebesgue measure, then use the fact that the Lebesgue measure associates 0 mass to singleton sets, and therefore you immediately get that the length or the size of the closed interval AB is the same as the left open right closed interval AB. Okay, so that's great. And similar arguments will then show that all these intervals, left open right closed or right open left closed or closed interval AB or open interval AB, all of these has the same size under the Lebesgue measure, and that is nothing but the usual length. So this basically completes that identification of the Lebesgue measure, that it associates the usual length for intervals. So we have already identified the length of intervals, and we have already identified the length or size of singleton sets or finite sets or countable infinite sets. But beyond that, what are the other interesting examples? But then you should note that there are uncountable sets in the Borel sigma field such that the length is 0. Okay, so we don't go into the details, but just for an example, there is this standard example called the Cantor set, and it can be shown that the Cantor set is an uncountable subset of the real line, and its length is 0. The Lebesgue measure associates 0 mass to Cantor set. Even though it is an uncountable set, it associates 0 mass there. Okay, so we are not going into the details because we are focusing more on probability aspects of it. So we will use this Lebesgue measure as mentioned in the previous lecture to discuss certain things about absolutely continuous random variables that we are going to see later on. So we are not going to use much properties of such Cantor sets or uncountable sets. Okay, so it should be good enough for us to know that there are such uncountable sets with mass 0. So this is just an interesting fact. Now let's move forward. Now recall the definitions of Borel sigma fields on Borel subsets of R. Okay, so if you focus on, let's say, this kind of an interval 0 1, closed interval 0 1, then you can define the Borel sigma field on 0 1 as follows. So this is the collection of subsets of 0 1 which are of the form A intersected with 0 1, where A varies over the Borel subsets of the real line. So choose all possible Borel subsets of the real line and intersect it with 0, 1. So you will get all possible sets that are inside the Borel sigma field. So that's how in fact the Borel sigma field on 0, 1, the closed interval 0, 1 is defined. Alright, but now what we are going to do is to construct a measure on top of this Borel sigma field of 0, 1. So what do we do? So we write it as this notation, lambda restricted to the Borel sigma field of 0, 1. So it will take any arbitrary subset of Borel sigma field of 0, 1 and assign certain values. So let us see this. So how do you define this first of all? So again, any arbitrary set in this Borel sigma field of 0, 1 looks like A intersected with 0, 1, where A varies over all possible Borel subsets. So what do? You simply look at the size of the set A intersected with 0, 1 under the Lebesgue measure. Okay, so just look at the size of this set and associate that value for this set function. So this set function that you define as lambda restricted to this Borel sigma field. What is going to happen is that this set function that you have just defined turns out to be a measure on Borel sigma field of 0, 1. Okay, so this is left as an exercise. So this simply uses the non-negativity of the Lebesgue measure that is already given to you. So these values are non-negative, and you then use countable additivity for a pairwise disjoint sequence of ANs. You apply it to the countable additivity of the Lebesgue measure lambda and prove the countable additivity for the restricted function. Okay, so please check that this restricted function becomes a measure on the Borel sigma field of 0, 1. But then you also should note that what is the size of the whole set under this measure. Okay, so it turns out that restricted function, this lambda restricted to 0, 1 of the interval 0, 1, closed interval 0, 1 is nothing but 0, 1 intersected with 0, 1 itself. This is as per the definition, right? So you just have to look at what is the size associated to this interval by the Lebesgue measure, and that is nothing but the usual length, which is 1. So therefore what you ended up getting is that lambda restricted to this Borel sigma field of 0, 1 becomes a probability measure on this measurable space. Okay, so you have verified this is a non-negative set function, it's countable additive by the properties of the Lebesgue measure, and finally you have shown that the length or size of the whole set is equal to 1. And therefore this example gives you certain nice ways of constructing probability measures from other infinite class of measures. Okay, other infinite measures. Okay, so in particular for Lebesgue measures we have seen this. But then you can repeat this construction or this statement for intervals of the form closed AB with length B minus A equal to 1. Okay, so in that case again you restrict it to the appropriate intervals, and you can again show that such intervals, if you restrict the Lebesgue measure there, you will again get a probability measure. Okay, so this will now be on closed intervals AB with appropriate Borel sigma field on AB, and there if you restrict the Lebesgue measure you are going to get probability measures. Okay, we are going to see usage of this later on, but now here is an interesting example. Okay, so now we are going to construct a subset of the real line which is not in the collection Borel sigma field. Okay, so therefore it is going to show that the power set, which is the collection of all subsets of the real line, this is strictly bigger than the Borel sigma field. So there are subsets of the real line which are not in this Borel sigma field, okay, which are not Borel subsets of the real line. So how do you show this? So this requires certain set theoretic arguments, specifically using certain things called axiom of choice and equivalence relations. If you use that, you can actually construct a sequence of sets, let's call them as AN, which are pairwise disjoint, and their union will cover open 0 to closed 1, this left open right closed interval. Moreover, we can also show that if you can choose the sets from the Borel sigma field, so a priori it's not clear. So if the sets are in the Borel sigma field, then you can show that the Lebesgue measure associated to these sets are equal. Okay, so all these sets have the same length or same size under the Lebesgue measure. So such a construction is possible provided the sets are inside the Borel sigma field. Okay, but then what is going to happen is this. So observe this equality. So you have the length of the interval open 0 to closed 1 is 1, that we have already seen. But if the sets AN are pairwise disjoint and their union is exactly this interval open 0 to closed 1, then use countable additivity of the Lebesgue measure to write it as this summation. Okay, summation from n equal to 1 to infinity Lebesgue measure of the sets an. But as we said, if the sets an are in the Borel sigma field, then what you can do is that you can show that the Lebesgue measure associated to these sets remain the constant, which we write as lambda of a1, the first set. But now you are led to a contradiction. So the contradiction is this: you are having a constant term, you are adding it infinitely many times. So it's a constant sequence, you are adding it up, and you are saying that the sum is 1. So now there are two possible choices which you can do. So if the Lebesgue measure associated to this set is 0, then the sum must be 0, so the equality does not hold. If this Lebesgue measure associated to this set is positive, then by Archimedean principle this summation will diverge and diverge to infinity. So it will not be equal to 1. So this leads to a contradiction, and therefore you will immediately claim that the sets an are not in the Borel sigma field. Okay, so this was the assumption that we made, and which we implied that you can talk about the Lebesgue measure of these sets. So that's the issue here. Okay, so if the sets are in the Borel sigma field, then you can construct such sets with same Lebesgue measure. Okay, so that is leading to the contradiction. So therefore there exists at least one such set which is not in the Borel sigma field. Okay, so again, to avoid this complexity of this construction of such sets, we are not going into the details of this. Okay, so but I am mentioning a reference here, so you can go to a book by Gerald Folland. The book title is Real Analysis, Modern Techniques and Their Applications. It's a second edition of the book. You can look at the chapter 1 of this. It's published by John Wiley, and so take a look at this if you are interested. We end this lecture by listing certain other interesting properties of the Lebesgue measure. So here you start with a point x in the real line and consider the continuous function that maps the point y to y minus x. Okay, so look at this function from R to R. So this is a nice continuous function. So now here are the steps in the exercise. So the first step says that you verify that for any set A in the Borel sigma field, the set A plus x can be written as the pre-image of the set under the function f. Okay, so you are given this explicit function, please compute the pre-image and show that this is A plus x. So now you will ask, what is A plus x? So A plus x is defined as y plus x, where y belongs to A. So here you are just shifting the set capital A by the point small x. So this small x you are fixing beforehand. So that's the first part of the exercise. So the second part says you should try to show that for all possible x in the real line and all possible Borel subsets, the set A plus x is also in the Borel sigma field. So that means that given any Borel subset of the real line, if you translate it by x, then you will get back another Borel subset. So A plus x is again a Borel subset. Please check this. Now using this observation, you can now define a set function. Let's call it as mu. So what you do is that you define the size of the set, arbitrary Borel set, as the size of A plus x, meaning whatever the size associated to A plus x by the Lebesgue measure. So you fix that point x, look at A plus x, look at the Lebesgue measure of that, that's some non-negative number, you associate that value to mu of A. Okay, so you get a new set function mu. You can try to check that this mu becomes a sigma finite measure. So this is on the Borel sigma field. But then interesting step is this, that you can now try to check that measure associated to sets of the form which are finite disjoint unions of left open right closed intervals. For such sets you can try to verify that the Lebesgue measure associates the same mass as mu of A. Okay, so for sets which are finite disjoint union of left open right closed intervals, you will get the same length or the same size under both these measures. Okay, so first observe this, verify this directly, and then using this you can try to show that for all Borel sets these two measures agree. Okay, so again we are saying that first verify it for left open right closed intervals, then for finite disjoint unions, and then for all Borel sets. Please verify this. But then what does this exercise finally say? Look at the structure of mu of A. So that is defined as Lebesgue measure of A plus x. But now you are saying that Lebesgue measure of A plus x is equal to Lebesgue measure of A for all Borel sets, right? So that's what this last part of the exercise implies. So therefore what you end up getting is that for any point x in the real line and any set in the Borel subset of R, you get that the Lebesgue measure associates the same mass as the Lebesgue measure of the shifted set or the translated set. Okay, so now we state this property of the Lebesgue measure as follows, that the Lebesgue measure lambda is translation invariant. Okay, so if you translate the set A by some point, you will not see any difference in the size. Okay, it associates the same size or the same length. Alright, so we have listed some of the very interesting properties of the Lebesgue measure. In the next lecture, we are going to see certain higher dimensional versions of the discussions that we did in this week. So in particular, we are going to discuss this connection between probability measures and distribution functions in higher dimensions, and we are also going to mention certain facts about the Lebesgue measure. Okay, so we stop here.